that helps us determine its production. And here we have the table on the next page, and you'll notice the way you read a table, of course, is first you read the title of the table, then secondly you check for any notes, and then finally you find an intersection of a row and a column, and you pull the information out, and you ask yourself, what does this mean? If you can answer it correctly, you probably understand what the table is about. If you can't, you don't have it yet. In this case, we're talking about the rate of a sheep's foot roller compaction in cubic yards per hour based on a 5-foot wide roller going 2.5 miles an hour with 12-inch lifts and 100% job efficiency. So for example, if I correlate the number of passes, let's say one pass, with tough clay, I will see the number 1711. What that means is that given the conditions of the name of the table, all of those conditions match, and given a one pass over this land, I'll be able to compact 1,711 cubic yards of material per hour. Now, what would happen if everything was the same, except that the machine was going twice as fast? Instead of going 2.5 miles an hour, it's going 5 miles an hour. What would you do with this 1711? You would double it. So problems dealing with this table, or tables like it, require that you match the characteristics, find the appropriate number, and then possibly adjust this number for differences between the specifications in the table and the specifications of the question. On the next page, they actually give us an example and then solve it for us, which can serve as a model for our own problems on the exam. It says, assume a fill to be placed in 9-inch lifts and rolled 8 passes with a double drum sheep's foot roller 10 feet wide at 2.5 miles an hour. So the first step is, it says we go back to that table and we correlate 8 passes in 80% material. And it's going to give us a value from the table of 245 cubic yards. It then tells us to adjust this for a 10-foot wide roller. Well, that means we're going to have to double it, because the 245 was based on a 5-foot roller. Okay, and that tells us that when we double it, we get 490. The next thing it says is we have to adjust it for 9-inch fill layers. Well, the table's based on 12 inches. So if we simply multiply the last value, the 490, by 9/12, we will have adjusted it for the shorter lifts. Then it tells us that we should assume a 50-minute hour, or a job efficiency of 83%. How did they get 83%? They simply divided 50 by 60. And after you do these things, your final number becomes 305, at which time they tell you to subtract another 10%, and you come up with a production value of 275 cubic yards. If you're given a question like this on the exam, your task is to simply find your way back to this page and follow it step by step. In fact, most all of the math problems on the exam will have examples in the reference books laid out somewhat like this. Another similar specialty problem dealing with heavy equipment has to do with the use of fuel. And we find this again in Walker's on page 2.32. And this is a relatively simple type of calculation. And the example is on the next page. 100 horsepower engine in shovel service is estimated to consume per hour 100, the horsepower, times 0.040, which is the assumption made for an average use, and that gives us 4 gallons. Turning back to our outline, we've covered under number 7 items A through G, and the next level of items deals with the transit and the level, and again refers us back to the principles and practices of heavy construction. What you need to know about this is 3 things. First of all, you need to know the difference between the two, and the difference is simply that a level only goes on the horizontal plane, whereas a transit can go vertical and horizontal. The other thing you need to realize is that occasionally the exam will ask you for components or some of the parts of these pieces of equipment. And you need to know that pictures and diagrams and labels and names are all found as indicated here in the Principles and Practices book. And then finally, you're going to probably run into a type of question that will require you to determine something about an unknown elevation. This is taken from the cram book on page 13A. We're not going to go through the entire problem. And you have some sample problems in your book that are a little gradiently easier than this one. But the point I just want to make is this, that the whole idea is if you can find out what elevation this line of sight is at, then when you look from the point of view of this line of sight at a location where you have an unknown elevation, and if you were to place a rod in that location, and this rod had numbers on it, you would be looking through here and you would be seeing a number. Well, for example, if you knew for sure that this line of sight had an elevation of, say, 10, and when you looked in the direction of your own unknown elevation and you put a rod on top of that unknown elevation and looked to see what number you would see, and the rod would be marked with 1, 2, 3, etc. And let's say when you looked through here you saw a 5. If you knew the line of sight was 10, and if you knew therefore there was 5 feet distance from that known line of sight at 10 to your unknown elevation, you'd be able to figure out that the unknown elevation must be a 5. The formulas that the cram book will take you through about this do that. And they allow you to set up a transit, to look at a known location first, where you will place a rod over a benchmark. You will then use the benchmark and add that to the rod reading, and that will tell you the elevation of this line of sight, which is called the elevation of the transit. You will then look in the direction of what you don't know, place another rod there, and from your knowledge of what this line of sight is, you will subtract the reading that you see in the unknown location, and that will tell you what the elevation of the unknown location must be. Returning to your outline, topic number 8, I'm just indicating here the different types of math questions that you're going to run into in this topic area. You're going to need to work with the area of a site, combine a ratio and an area. You're going to have to deal with volumes and areas, and the basic shapes are squares and rectangles and occasionally a trapezoid. You'll need to know how to deal with an OSHA pit, that is an excavation where the upper edge is sloped back in all 4 directions so that it does not cave back in on the people working inside of it. Another type of question that you might be asked about is steel sheet piling. You also will be asked perhaps about property line angles, how to figure out a property line angle. And then, as we indicated earlier, setting elevations. And all of these are covered as indicated in the cram workbooks. And you have sample problems in your 20-question exam at the end of the module. Do the sample problems first and see how you do. From there, you'll know what additional information you'll need to research. The next topic in your outline, Roman numeral 2, deals with footings and foundations. There's not a great deal of detail here, but if you'll notice on the outline itself, one of the first issues involved in laying out a building is the nature of setting the building corners up and verifying that the building is in square. Now, your first couple of chapters in the Principles and Practices of Heavy Construction show you how to go about and assemble batterboards and how to draw strings across the batterboards that indicate where the footing should be dug. If you look in the cram workbook, you will see a math problem that corresponds to this idea of verifying that a building's in square. And essentially all you're doing is finding the diagonal of the building corners. The second topic under this general topic of footing and foundations is just some basic information about footings. And this comes primarily from the Southern Standard Building Code. The first thing is that, of course, here in South Florida it's not much of an issue, but around the rest of the country, frost is an issue. And what it indicates here under 2A is that the bottom of the foundation has to extend below the frost line so that we don't have a foundation that's not adhering to the soil in a stable way. And also you'll know that the degree to which the foundation must extend below the frost penetration level is 12 inches. Item number B indicates that excavations shall not extend within 1 foot of the angle of repose. What this means is very simple. If I have an existing building, say this building is over here, it's going to have footings underneath it. And if I were to draw a 45-degree line against the outside edge of the footing, that would be the angle of repose. And what they're telling you here is you don't want to dig next to that building in such a way that your excavation assaults that angle of repose. You got to keep 1 foot back of it. Otherwise, what can happen is in the process of excavating for your project, you will undermine the project that's next to you. Item number C deals with waterproofing and indicates that the top of the footing, not less than 6 inches, needs to be waterproofed. There then are some questions about the nature of piles and how you calculate the amount of a particular pile to carry, the load on a pile. And we'll be looking in the reference book in the appropriate place on the principles and practices of heavy construction for that. And that's an example of a problem that you'll have in your sample problems at the end of the module that you want to see if you can take a crack at it and see how it goes. And then finally, topic E, there's some plan reading that'll be involved here. And all we want to point out at this time is that Walker's has information about plans, about plan reading. It has symbols. It has the definition of architectural perspectives. It has the definition of engineer scales, architect scales, and how to translate between them. And you need to know that this information exists. Later on in the last module, we will go into more detail about actually reading plans. But for now, recognize that there are bits of information in Walker's in the first chapter. Roman numeral 3 in your outline introduces the subject of concrete. And what I'd like you to notice on your outline first is that one of the elements in concrete is cement, and that there are different types of cement. And these are listed on page 15 of Design and Control of Concrete Mixtures. You'll need to be somewhat familiar with these types and understand that these are different aspects of cement. And it would be incorrect to refer to a type 1 concrete, even though that's done all the time anyway. The point here is that these types are the normal ones encountered, although concrete could be designed for other purposes and could be separate from this particular listing of types. Another exhibit that's in your package is this exhibit entitled Understanding Concrete. And we're going to talk our way through this exhibit, and then we're going to go back and take a look at the outline. And I think by seeing it pretty much on one page, some of the major points, it's going to help you understand what this concrete issue is all about. Understand first that concrete is an engineered product, and that means that it is designed under controlled conditions when it is produced. It must be under controlled conditions when it is transported. It must be controlled when it's placed. It must be controlled also when it's finished. And there may be special applications for the concrete. Now, what this outline does, this exhibit, is it shows you where these topics are proportioned in terms of the chapter of the book. And the book we're talking about here is the Design and Control of Concrete Mixtures. And the first thing we want to take a look at is the manufacture of concrete. And the first topic here we're going to look at are the things that go into concrete to make it what it is. And when you think of concrete, it will help you if you think of a milkshake, because that's really what concrete is. When it's manufactured, the specifications for the milkshake are followed, and it is created exactly as specified. From that point forward, the entire goal is not to allow the milkshake to disintegrate into its components, to keep it in the same condition as it was when it's created. And that's why there are rules about how it's transported, placed, and finished, to keep the milkshake consistent. Now, the terminology that's used is segregation. You don't want the concrete to segregate. You don't want its parts or components to fall apart, because then you will not have a uniform mix. Now, regardless of the type of cement that's used, the basic components of concrete are water, cement, air, aggregates, which are big and little rocks, and then admixtures, which are additional chemicals which are introduced to the milkshake to provide specific qualities to the milkshake. If you take a look at the first chapter, the first page of the first chapter, Fundamentals of Concrete, in the Design and Control of Concrete Mixtures book, you'll see the typical proportioning of concrete. Now, what they're showing you here is air-entrained and non-air-entrained. The word entrained just means added. Air-added concrete means that you've got a milkshake that's particularly fluffy. What this does is what you might expect. Air has an insulating quality. It also tends to make something plastic. And so air-entrained concrete has a higher insulation value. It resists freezing and thawing cycles, so it doesn't crack quite as much, and it's a little bit more plastic. However, be that as it may, they're showing you the relative proportions of the basic components of concrete. We have cement, water, air, fine aggregates, and coarse aggregates. And they're showing you how these are proportioned. Turning back to the handout, we'll take a look at these components and see what they mean. The first one is water. Water is both a friend and an enemy to concrete. Water is necessary to create hydration. The chemical process of hydration is the process of the milkshake hardening. Concrete takes a long time to harden, approximately 80 years. So that slab you poured a year ago is still getting harder and harder. It's still hydrating. And this process will continue for a long time. If you don't believe it, go to an older slab and hit it with a hammer, and then try that with a new slab. The older slab, you're going to hurt your wrist. On the other hand, water is an enemy of concrete because too much water destroys the milkshake. There are rules as to how much water can be added to a mix, and there is a tendency in the field for individuals to want to add water to make it easier to move the concrete around and put it in its final position. These tendencies are to be resisted. There must be an exact amount of water for the mix, and this water really should not be varied except under controlled conditions. The next component is cement, the actual sticky stuff. Now there is a ratio that relates one component to another, and later on we'll see, and in the outline you'll see the specific page, where we have a water-cement ratio. Now remember that when I say a ratio, I mean one number divided by another number. When I say water-cement, what I mean is that water is on the top and is being divided by cement. So let's say I had 1 unit of water and 1 unit of cement. The ratio I would get in that case would be 1 to 1. But let's say I changed that and I had 2 units of water and 1 unit of cement. My ratio there would be 2 to 1. In the second condition, where I had 2 units of water for every 1 unit of cement, would you expect that concrete to be softer or harder? It would be softer. It would be soupier. And therefore, the higher the number in the water-cement ratio, the weaker the substance. Another component is air. We've talked about air before. It provides insulation. It makes the concrete more plastic, which therefore resists freezing and thawing and resists cracking. Aggregates are subdivided into big rocks and little rocks. The significance of the aggregates has to do with the surface area of the stones. If you had a big boulder and you measured its surface area, and then you broke it into little pebbles and measured all of their surface areas, which would have the greater surface area? All the little pebbles. Therefore, there would be more to stick to, and therefore, the smaller the rocks, everything else being equal, the stronger the mix. That's why when you use a chat mix or a higher compression concrete, it will come with smaller rocks, because that will affect its strength, because there's more surface area for it to bond to. And then E, admixtures. These are components that are added to the mix to get special requirements. And notice that these topics are talked about in chapter number 1. Now there are certain key characteristics of concrete that get measured. The first is the curing rate. The second is the strength. The third is the freeze-thaw cycle. The fourth is permeability. Now permeability relates to the durability of the concrete. The more permeable the concrete, that is to say, the more open it is to be infiltrated with other substances, well, the more that other substances are going to infiltrate it and break the concrete down. So permeability is an issue that deals with longevity. And then we have the issue of stability and whether or not the concrete is going to have a tendency to crack. Chapter 2 now introduces the types of concrete, which we've discussed earlier. It talks about a special type of milkshake where extra air is added. It talks about specialty types. And then it talks about the relationship between masonry cement, which is sometimes also referred to as grout, or stronger types of cement, or concrete mix, which are also referred to as grout. Chapter 3 deals with types of water and their effect on concrete. As an aside, you may notice this, in the early 1900s, there was a period of time in South Florida where they ran out of sand. Well, what happened was they went down to the beach and they used beach sand. And now, on those houses where that was done, you can go around that house and with your finger, you can start scaling the house away and it won't stop. it'll just keep scaling because that type of water and sand, non-standard, created additional problems to the mix, and now those units are deteriorating. Chapter 4 deals with aggregates and the way in which aggregates are found and classified and measured. Chapter 6 deals with admixtures. They break down into retarding admixtures and accelerating admixtures, the effect that some of these have on the freeze-thaw cycle and the workability agents. And number 10 deals with proportioning the concrete. And the first issue with proportioning the concrete was one that we mentioned earlier, the water-cement ratio. If you look on page 78 in my edition, table 7-1, here we have a table that's significant because it indicates the maximum water-cement ratio for various exposures. So for example, if I'm dealing with water that's concrete that's supposed to be exposed to fresh water, then I'm going to want a 0.5 to 1 water-cement ratio. And you may be asked a question that deals with a quantity. For example, by weight, if I'm dealing with a 0.5 water-cement ratio, and I know I'm going to be using, say, 1 cubic yard of cement, how much water would I need? A relatively straightforward calculation, but you'll need to be able to work that sort of thing out. As indicated earlier, this water-cement ratio affects the compressive strength of the concrete. And on page 79, we see a table to this effect. We also see the distinction between air-entrained and non-air-entrained given a particular water-cement ratio. Now, one of the things that's of interest in this book that's different from some of the other reference books is that the tables in this book, in addition to being similar, some of the tables are similar to the kinds you've seen before, you also see a table like this that kind of shows you a three-dimensional idea. And you might want to take a look at some of the tables in this book and make sure you can interpret what these tables are saying. It may take you a time or two to look them over. Returning to our handout, the second major topic dealing with concrete is its transport. And as we said, there are controls over its batching, mixing, and its transportation. And then the next subtopic here deals with certain methods and tools that are used in the transport of concrete. The next topic deals with the placement of concrete. And again, the whole idea here is you do not want the mix to segregate. You want that milkshake to stay consistent. You can place concrete with buckets or with chutes or with buggies. If you're going to use a chute, you do not want a more than 1 to 3 rise-to-run slope. If you use a long chute, more than 20 feet, you want a hopper in between that 20-foot section and the next section. Chapter 9 tells us we want to place this concrete as near to its final position as possible. We want to avoid segregation. We may need to use drop chutes so that the free fall does not exceed 3 to 4 feet. This is an important point if you're pouring columns, because you don't want the concrete to splash on the ground. That will separate and segregate it. Another issue that's important when dealing specifically with column work is the size of the aggregates. If you've got a bunch of pieces of rebar stuck in a column, you have to consider the idea that the concrete won't fit if the aggregates are too large. Another issue has to do with how do you make sure that the milkshake stays consistent. And one way you can do this is through vibration. And one way to create vibration is to use an insertion rod, which you would extend 6 inches into each layer with a 12-inch maximum layer. And you're going to want to move this very slowly, dropping it all the way to the bottom, at least 6 inches into the next lowest layer, pulling it back up very slowly, and then going no further as you move it along than 1.5 times the radius of action of this vibrator. In addition to this, there are form vibrators. For example, that column I spoke of a